Hello everyone, and welcome to Spectral Geometry in the Clouds. Today it is a pleasure to listen to Matthias Hofmann, who will talk to us about the graph structure of the nodal set on Riemannian manifolds. As usual, don't hesitate to ask questions, even during the talks. If you do ask them in the chat, we will relay them to the speaker. Here we are. Matthias, the virtual floor is yours.
So thank you for giving me this opportunity to speak today in your seminar. I will start right away with the roadmap and what I will be talking today about. So we start with the general introduction to what is known regarding nodal partitions or eigenfunctions of the Laplace Beltrami that we're going to look at, and then we're going to talk about how points that vanish in some sense are particularly interesting. So we're going to introduce a so-called vanishing order for these points, and then we're going to talk about how the nodal set has some kind of graph structure, and then how we use that to derive some kind of global estimates on the number of critical points and this vanishing order. Then we're going to talk a little bit about proofs, and then we're going to give some examples to kind of talk about sharpness of the results. And then I finish with some comments on where this whole research could go to. So for the setting, we have a Riemannian compact orientable manifold, no boundary, and then we're going to study the Laplace Beltrami on it, and we're looking at an eigenvalue problem. So now introducing a smooth potential, and I didn't write it. So without lots of generality, q greater or equal to 0, then one can show that. Okay. Also, I guess this was the mistake. This should be small or equal. So then we can order the eigenvalues, and the eigenvalues will go to infinity by general spectral theory for the Schrödinger operator on such a Riemannian manifold, and we denote by sign an orthonormal basis, eigenbase, orthonormal basis consisting of eigenfunctions to some eigenvectors that be to these eigenvectors on the end. Okay. So what is a nodal set and what is a nodal domain? So the nodal set of a continuous function is the set where the function becomes 0, so it's a 0 set. And if we remove the 0 set, the connected component that we are left with is what we refer to as nodal domains. And if we count the number of such of those connected components, this is the nodal count. And so Current's nodal domain theorem says that the kth eigenfunction, and this is based on some kind of variational arguments, can have at most k nodal domains. And so the special set that we are interested at is the critical point sets within this nodal set. So these are the functions where the gradient becomes 0. Okay. And so what is known for the nodal set under this setting that we study? Well, first of all, it is known that the number of critical points is finite. And then the nodal set consists of this finitely many closed C2 curves. which can only intersect at critical points. And those critical points are characterized in the following way. That is, whenever two or more such curves meet, we will have this critical point, and they form an equiangular system that is locally, they consist of two n arcs, each having angle pi over n to each other. So this originally in 2 dimensions was done in a doctoral thesis, as far as I know, by Albert, and then later in a more general framework was generalized in a lot of directions, but in particular they recovered this result. So how is this related with this vanishing order that I talked about? So now you can ask, so if we have a critical point, we can denote now the number of the highest n such that all the partial derivative lesser than order n vanish. And it turns out that this number is actually characterizing exactly the number of arcs that meet at such a critical point. So this is part of this study that was done by Albert and Schr. So if we are in the node set and it's not a critical point, then it's always vanishing of order 1. If it's a critical point, it's always at least a vanishing of order 2. And it is exactly equal to n½ where n is the number of arcs of the nodal set. And this number will always be an even number, so this is always going to, I mean, like you see by definition, the natural number. And now, so what, why do we relate this with the metric graph? So I'm particularly coming from this community on metric graphs, quantum graphs. Quantum graphs not so important in this case, since we're just interested in topological features. So a metric graph consists of this family of intervals that we join together in this kind of network-like fashion. So you have this kind of like partition of the endpoint set like here, and then you get your graph this way. And then in a sense, this is exactly what we have here with the nodal set, because so this is, so now reducing the properties that we found before just to the topological properties. So the nodal set consists of this finite number of connected components that each component either is homomorphic to a circle or it is homomorphic to a finite number of closed arcs, which are basically some type of intervals, and they are exactly joined together at this critical set. And so every point in the critical set, this is the property regarding how these arcs meet at such critical points, consists exactly of this even number of arcs that are adjacent to it. And at any at any vertex, at least 4 such arcs need then to end. And so if we want to give now meaning to a graph structure, we can do that in the following way. So V, the vertex set, is basically the critical set. The edge set would be the arcs between critical points, and the faces, as we embed it into this manifold, will be exactly the nodal components. Okay. Now, what we wanted to do is find some kind of global relation between these quantities. And the kind of issue that one has is, first of all, the failure of connectedness, but also the failure that they do not necessarily need to be cellular embedded. So when you have a cellular embedded graph, that is, all the faces are homomorphic to this, then you have a cell complex, and therefore you have this Euler formula, which just depends on the genus of the manifold. And so what we try to do is, given the structure that we have, construct modify the structure in a way that we can apply this result that is known for cellular embedded graphs. Okay, so these are our main results. So first of all, we have a number on, we have an upper estimate on the number of critical points. So it's bounded by the number of nodal domains plus the Euler character minus the Euler characteristic, or plus minus. And the second result that we have is regarding the sum of all of the degrees of the critical points, which is related to the vanishing order of the eigenfunctions at these points, which can be bounded by this 4 times number of nodal domains minus 4 times the Euler characteristic. And so if we combine this with Courant's nodal domain theory, we get this nice inequality for the number of critical points for any given case eigenfunction that which tells us a little bit about how such a case eigenfunction can look. Okay, and similarly, we can also do that with this sum of the vanishing orders. So I already kind of described how the proof works. So, and it took some time for us to kind of find the correct way to do this. So we came up with this 3-step strategy. So the first step is, so the first problem that we came to mind is that the nodal set might not be connected. So this is the first we want to do. So I suppose we have this union of metric graphs, connected metric graphs and circles. How can we make them connected? Then the second step is we might still end up, even after we connected all the nodes set, we still might end up with something that is not, so this is different to the planar case, for instance. So in the planar case, at the moment you make everything connected, each of the faces will be homomorphic to the disk because they're simply connected. But if you're on a general manifold with handles, you might have some handles that cause non-trivial fundamental groups, and that's why you have problems. So the first step to simplify the problem is to reduce the boundary to a single connected component. That's our step 2. And the last step is to make the faces homeomorphic to this. Then, so after we have only a single connected component of the boundary, we just have to think how we can deal with these angles that are attached at a single hole in some sense. Okay. So let me kind of sketch by picture how the proof would look like. So suppose we have n many connected components, then in order to make them connected, we need to add n-1 many edges, n-1 arcs between these connected components. And so what one needs to realize, what one needs to realize is when connecting such these two connected components, we do not disconnect the nodal component, because as I sketch in this image here, one can basically go carefully around such a connected component of the nodal set after drawing this line, and it will still provide us such a bridge between the two sides here. So because of this, we can we only change the number of edges and the vertices, and
Matthias, there's a question in the chat right now from Remy,
please,
who asks, why is there a need for the graph to be connected? Why is it not possible to perform this with a disconnected graph?
Well, if you have a disconnected graph, the question would be what the Euler formula would be. So you have a formula for disconnected graphs in the planar case, but I don't know. As I looked in the literature, there was very limited information regarding how to deal with disconnected graphs. That's why we connect them. Also, this allows us to really get the metric graphs, because now we open up circles. Of course, we can always study circles as a type of metric graph by introducing these dummy vertices. Of course, that would also work. So what we get basically for every single disconnected component that we have. So we need to introduce this n-1 additional arcs between them. So this will be like the surplus. Yeah, I think there's a mistake with these numbers, which I'm surprised I didn't notice this. Okay. So step 2 is making now the faces have connected boundary, and so I will just maybe quickly draw this, because I didn't have this in my in the work. So, a picture for this. So suppose we're like in this previous situation where this is what we connected, and then we have another connected component so the node set might still be connected, but outside of such a nodal component. And so if we want to connect them within the nodal component, of course we can do that just like in the previous step. pick a vertex and connect it back within the connected component that doesn't cause any issues. And so this is just an additional step that one can take to kind of avoid having topologically more than one hole. Okay, so this is the second step. Okay, really delete it. And now what we're left with is basically just handles. Handles means that so anything that is not now homomorphic to a disk is really a connected sum of tori. And how can we cut off these tori? By introducing a number of vertices and number of edges. So we didn't make this more precise how many times we would need to do this, but of course it's only finitely many times up to the number of up to the genus that you have. So this is at most how many such surgeries you would need to perform. And in every single step in order to cut away such a handle, we need to do such an operation where we open the handle by making a hole on the other side of it and then drawing these connections. And so this gives us these 4 additional edges. I have to review the proof if it's 3n here, really, because it looks like 2n. The images might be probably misleading, but in any case, you can control the number of edges, control the number of vertices that you get in every step by cutting away such a tori. And if you combine all of this, you get a graph that is now cellularly embedded, not circularly, cellularly embedded graph. And we get now this quantity that has basically a finite remainder, and this finite remainder we'll see we can just bound away in the next step. So how do we do this? So we use the fact that we know that the degree of every vertex in our graph is at least 4. Why do we know this? Because every critical point is incident to at least 4 arcs. And this gives us then that the number of edges, which is exactly half of the degrees of the vertices summed together, has to be then greater or equal to 4 times this number of critical points divided by 2 gives me then 2 times this number of critical points, which is my V. And then I can use the Euler's formula here, replacing bounding away E by 2V, and I get then that F is greater or equal to minus 2G plus V. And so what do we want to bound away? That is the number of critical points. So we we bring 2 minus 2g on the other side, and then we get this bound for v in terms of f, where f is the number, the nodal count, and v is the critical, number of critical points. And now regarding the inequality for the sum of the degrees of the vertices. So now, again, we have here, this is actually inequality, and we can do the following trick. We bound away half of it by the previous inequality. Now we get the v, and the v will cancel away, and we end up with now an equality of f against this sum of the degrees, and we get therefore that the sum of the degrees is bounded by 4 times f plus minus 4 times this Euler characteristic. Okay, and so with the interpretation regarding the vanishing order, we will get these kind of global estimates on the vanishing order and the number of nodal domains. And now I want to end up with some examples, also discussing the sharpness, and also so one nice model that actually where these kind of nodal partitions are used, and the only one that I actually know in the sciences is this atomic orbital model. So if you look at the spherical harmonics, you can describe them as this product between these Hermite polynomials and the cosine and the sine or constant function. So and all the eigenvalues of this form L times L plus 1, and we have then for every eigenvalue multiplicity 2L plus 1, and the eigenvalues, eigenfunctions. So one way to plot them on the sphere is to just plot their absolute value, the distance to the to plot the distance of the absolute value in angular direction at any point. And so what you see here, which are these orbital models that you might know from chemistry, exactly come from then assigning a light color for one sign and a dark color for the other sign of the eigenfunction. And so you see how you have this kind of atomic, these atom models that you might know from school and which are used in sciences. More conveniently, if we plot the nodes of these eigenfunctions, we can actually see some kind of phenomenon. So in the case where the absolute value of m is 1, this is this case on the left, every single critical point, so we identify them here as these crossings, is exactly of degree, so has vanishing, or is of degree 4, so has vanishing order 2. And so one can show actually that this leads to strictness in our estimates. So because we are here in a nice scenario where the node set is then exactly going to be our spherical embedded graph, we don't have any problems, and all these estimates that we made, there was nothing to estimate away. Everything was equalities. That's why we get here the sharpness. And on the other hand, if we have this type of meeting point, so now we get few critical points. Obviously, we don't have any more sharpness in our inequalities. And also, these will be points of a high vanishing order. So one byproduct that one sees is also that this vanishing order can become arbitrarily large. In this example of the spherical harmonic functions, for example. On the torus, it looks a little different. So one way to get the eigenfunction is with this kind of tensor product. And it turns out that if one reduces this problem using this tensor ansatz, you are able to reduce it into two types of periodic problems on the circle essentially, and the eigenvalues can be then easily determined as kind of the sum of the square sums of the individual frequencies that you get from your tensor ansatz. It's very similar than what you would get, for instance, on rectangles. And so here, of course, one has then the same scenario. Every single crossing, so these are these points, will have degree 4, vanishing order 2, and you get sharpness in your inequality. But, so this is a kind of additional thing that we were not sure if this is known or not. One can actually show that for every n, one can find linear combinations where these linear combinations have very large, arbitrarily large vanishing order. So we can, using linear combinations, we can enforce very strong crossing. It can be shown that then the eigenvalues need to be very large, right, for this to happen. But it's an interesting phenomenon that even though you have kind of this, you have strictness, sharpness in the inequality for the individual eigenvalues, you will not necessarily have that for linear combinations thereof. And now I want to finish with where we might want to look at in the future. So the first thing that comes to mind is studying manifolds with boundary. So if you study manifolds with boundary, it's actually not too difficult to see that in general, upper bounds on the number of critical points are not possible if you include the boundary. So then the question would be, are you still able to recover something like bounds on the number of interior critical points, or if you have additional information regarding, let's say, the homology, if you can say something of the number of critical points. So this might be an interesting question. And then we have that, so these are all global estimates just using the graph structure, but there's actually a little bit more known, such as local results that we did not use. So that we wonder if there's anything that can be shown using local estimates. Usually this whole regularity theory, structure theory is always local. And you have this kind of estimates on number of the vanishing, the maximum of the vanishing degree, for example. And then another thing that one can show is, for example, that you can get this kind of quotient that's related to Pleyel. So, of course, the number of critical points over K is bounded above because the bound that we obtained is kind of grows like K. We can just add new UK below and above, and then we get exactly this Pleyel quotient as for a bound on the right side. And yeah, so we see that we have this kind of Pleyel inequality. I don't know if one could say anything about this quantity, or if anyone is looking at this quantity. And then another interesting direction, this is something that actually Rami Band pointed out to me, is also that one could ask if one could try to use these type of methods on Neumann partitions. So we haven't done that. So these are the kind of things that we want to look at in the future. And then that was it from me. Thank you for your attention.
Thanks a lot, Matthias, for this talk today. We have time for some questions now. So if you have questions, either ask them in chat or unmute yourself and ask them directly.
May I ask a question, please?
Yes, please.
Of course, Susie.
The question is to look at the problem from a different point of view. That is to say, to find those systems which do not have any or very few or whatever about a small number of critical points at all. I think this is connected with the problem which once Bogomolny introduced, and this is the connection between the counting of nodal domains and the percolation. In his model, there was no critical points. So the question is, can you tell me, did anybody think about what happens with what should be the condition for having no control points? No critical
little
points at all.
multiplicity. It should
Sorry?
be having little multiplicity. I think there are partial results in this direction. I would have to remember where I saw this. So there's partial results regarding this on bounds on the multiplicity. How if you have little multiplicity of the eigenvalues, you will not have a lot of critical points. So critical points are somewhat related to high multiplicity. So generically,
Right.
you shouldn't even see
Because, and this gives you the freedom on taking sums or linear combinations of the different ones, and then you get any shape that you want,
right,
like they do on the sphere.
Again?
If you have the symmetry, which brings usually the multiplicity of the eigenvalues, then you have to add up the independent solutions to get the general solution, and then you can find coefficients which give you any shape you wish. And then if you look at the pictures that people did, I think that in the book of what's his name, Heller, you find very nice pictures of those situations in which they chose on purpose a very special set of coefficients, and then everything percolates without any critical point at all.
Even the opposite might happen. So if you have high multiplicity, you can actually avoid critical points. Is this something you refer?
I never thought about it, but it just occurred to me that it is something that you might be interested in.
Yeah, multiplicity is something that could lead
Excellent.
to, at least it's a phenomenon regarding this high. This is also bind on the torus. We can find these eigenfunctions with high vanishing order, because
Sure.
put together a lot of eigenfunctions, you can force very high vanishing order because you can control all the derivatives essentially. You have very high multiplicity. So it really was a result from number theory essentially to show this. It's known that you can find numbers that are sum of squares in arbitrarily many ways.
Thank you for the question. Do we have other questions for Matthias? All right. I think that is all. Thank you very much, Matthias, for the talk this week.